Hello everybody. Today I'm just going to run you through how you can add 2 or 3 or 5 or 12 vectors, and it really doesn't matter how many, and it doesn't even matter what angle they form when they're tail to tip. So you would use this if ever you know you cannot do a right angle vector. Okay, so we'll get started with this problem here. It's a situation where we have two forces acting on an object in outer space. So two forces are acting. One of these forces is pushing or pulling with a force of 195 newtons, and that's in a direction of 138.5 degrees. So if I try to show where that is, not that we need to do this graphically, but if I just kind of want to give you an idea of the setup, I'll get a protractor here. Then that would be a vector that would be 195 newtons, and it would be off in this direction here. So just a little shy of 140. Okay. The second vector that's acting at the same time on that object is a greater push. It's 282 newtons. It's got more magnitude, and that is in a direction of 184.5. So again, if I just to illustrate that, if I go ahead and spin that around, okay, so from here to there would be 180, so I need to go just about 4 degrees more, and that would be about there. Okay, so I got my two vectors. Let's get rid of that. And we know that if I try to do these tail to tip, there is no way they will form a 90-degree angle. Okay, I could either, for example, try to set it up that way, keeping in mind that the order you add them doesn't really matter, and that's clearly not a right triangle, right? Or I could have instead put that one tail to tip. I still get the same answer. Either way, we know it's not a right triangle. So when you get this situation, this is when you want to go to the components method. All right, so the components method, remember, is a situation where you just find the x component of all your vectors and you add them up, and you find the y components of all your vectors and you add those up. Okay, so this is easy to organize in a little table where you can start to do that. So I'm going to go ahead and put all my x components here, and then I'll put all my y components here. And you want to do the same thing right now as you follow along on your piece of paper. Go ahead and set that up. There we go. And the base idea, what you're going to attempt to do, as I said, is you're going to try to find the x component of A, and you're going to add that to the x component of B. Now, if I had a third component, I could call it C, I would add that as well. If I had a fourth component, I would add that as well. So you can go on and on, but for this problem today, I see that I only have two problems. So two vectors. So I'm going to add those up, and remember, they are going to give me the x component of my resultant. I'm going to do the same thing over here as well in order to find the y component of my vector. I'm going to call A, and I'm going to find the y component of my vector B, and I'm going to add those up as well, and that is going to give me the y component of the resultant. Okay, so that's how the component method works. So I'm just trying to get organized here to keep track of my components and what's what. Make sure I do it. And you really want to do the same thing. If you're doing a test on your scrap paper, you'd set up a table like this. Okay? All right, good. So now that I am set up, I'm going to go ahead and start this work. So what are my two components? Well, this vector here, which I'll call vector A, I'm going to make the 195 Newton be vector A. Or I could have made the 282 be A. It really doesn't matter. You'll get the same answer. But I'm going to do the 195. And I see that it's 195 at a direction of 138.5. You'll notice it's already in the proper mode for me. So it's 195 newtons at a direction of, right, 138.5. Good. Okay. So if it's already in the physics system like this, then you don't have to do any translation. I don't have to put it on an axis and figure out, you know, what would the true physics angle be, because this is already in that system. So that part's easy, right? Okay, so If I call that my vector A, then remember what we have in our notes is if you're trying to find the x component of any vector, unknown vector, it's cosine times its physics direction, right? Now in this case, instead of r, I'm going to call this, since it's my vector A, I'm going to try to find the x component of my vector A, okay? And what do I know about this vector? Well, I know that it's got a magnitude of 195 newtons, so I'm going to multiply that by cosine of its physics direction, which is 138.5 degrees. Cool. And so let me get my calculator here. 146.0463656. Careful I don't pre-round here because I need to later on add these in something else. So I'm not saying I'm going to carry out all those digits, but I'm going to carry out a lot of them. Okay, so now I know the x component of A is negative 146 point. I think I'm going to go to 3 decimal places. I find that's usually good enough. Good. All right, let's see what the x component of the next vector, and the next vector, remember, is 282, and it's in a direction of 184.5 degrees. Let me go to my scrap paper here. All right, so what would that be in this case? That's going to be 282 newtons times cosine of 184.5 degrees. All right, cool. So let's figure out what that is in my calculator. And I get negative 281.1306881. All right, well, I don't need to go quite to that precision. Close enough. All right, well, good. Now I have my x components of the two vectors, vector A and vector B, so I can simply add them up, and that's going to give me what the x component of my resultant is. You guys can double check my math on this. I got 427.177. So that is my x component. Now that means that these two vectors added together, how much of this vector B is pushing in this direction and how much this vector A is pushing in this direction. Put it together, it's a pretty big push to the left, and that doesn't surprise me because looking at the tail to tip, I can see it's really far to the left, therefore a big negative quantity. Okay? All right, moving along, it's time for us to go ahead and figure out our y components. So let me go to my scrap paper. All right, so let me erase that and restart my scrap paper. As you can see now, it's prepared to solve for y components. And so in the vector that I chose as A, that was the one that had 195 Newton magnitude with a direction of 138.5 degrees. So I plug in my calculator, 195 times sine of 138.5, and I get 129.2109094. So that would be the y component of my first vector. For my second vector, if I want to find out its y component, I'm going to take its magnitude times sine of its direction. So go ahead and do that. 282 is its magnitude, its direction is 184.5. Put it in my calculator, and I get negative 22.125465. Cool. So I'm going to take these two, put them into my chart, which you can see I cleaned up a little bit here, add them up, and I now have the y component of my resultant. And so what we've done is now I have two sides of a right triangle. I really don't care about this original tail to tip and this complicated triangle. That doesn't matter because now I can make life really easy. I'll create a new xy axis, and because it's negative, it'll go in this direction. Okay, so that would be my x component, which is the 427.177. And the y component of my resultant is going to be up because it's positive, 107, not negative. It shouldn't be as long. It's going to be a little shorter, so it might be up like about that. Okay? And that is my y component, the 107.085. So I have these two, and the nice thing about components, keep in mind, components will always form a right triangle. So I know that this is a right angle that these two form. And therefore, when it's time for me to put in my resultant, now that I know my x component and my y component, I'll do this in a green vector here, I know that it is the hypotenuse of a right triangle. And so that's pretty easy to solve the magnitude, because the Pythagorean theorem says that the magnitude of my resultant, which is right there, r, equals square root of 107.085 squared plus 427.177 squared. So go ahead and stick that in my calculator, what you see here, and round it to 3 sig figs, because if I look, all my original forces were in 3 sig figs. I get 440 newtons. So I figured it out, and it was so much easier instead of this crazy tail to tip strange triangle, simply by having an x component of my resultant and my y of my resultant, which I got through component addition. It's a lot easier way of figuring that out. I just have one more thing I have to do, though. I have to give the direction of the vector, and we have to be careful here, because remember, direction is always measured from the positive x and counterclockwise. So I know that it's going to be greater than 90. It's going to be somewhere between 90 and 180. But I have no way of finding that out, not directly. What I can do is figure out this angle that is in the triangle. I can do that. There's possible for me to pull that one off. So if I can figure out what that angle is, this little angle here, okay, then all I'd have to do is take 180 minus theta. 180 minus theta, and I'm left with this piece of the pie. Okay? So how do I get this theta? Well, the main thing you're going to do for almost all these problems is inverse tan, and that's because you'll always, with components, know the opposite side. That's going to be your y component, and you'll always know the adjacent side. That's your x component. Since you'll always know those two, inverse tan is the way to go. So the inverse tan of my y component divided by my x component is 14.073. Therefore, the direction would be 180 minus 14.073, which is 166. So the final answer, if I wanted to write this correctly, would be my resultant is 440 newtons. I put a decimal there to show it's 3 sig figs at a direction of 166 degrees. And that's it. That's how I do it. All right? All right. Happy trails, folks.